teaching got a lot of attention. So let me point you to two other things. This is my new book, Physics of Computing. I've got all the overheads on the website. This book is a very different view of how to look at digital design. It goes from devices all the way up through architectures. I designed this book for a new class at Georgia Tech. It's a required course that replaces VLSI design, and thermal is a critical element of the material in this new course. I've come to believe that if you don't understand thermal, you don't understand digital design. And to support this book and my other books, I've got my Embedded Systems channel on YouTube. Okay, so this is just the intro to the channel, but there are, I don't know, a couple dozen videos there, and I can't read any of this stuff. But you can get, the channel has several dozen videos that talk about embedded systems. They talk about physics of computing and so forth. So you can look there. And my rate monotonic scheduling video has something like 10,000 tips, so it's pretty well. Okay. Next, let's talk about GPUs. Okay? We'll talk about architectures, programming in general. We'll talk about specifically how you do it for CNNs, and we'll spend a little more time thinking about the training problem, because this is the most computationally intensive part of using CNNs, and this is also where GPUs made their initial impact in this field, is by allowing enough training to be run in order to give good results during the classification phase. Oops. Okay, so GPU stands for graphics processor, but as you know, it evolved into a scientific computing platform because the algorithms you run for graphics are similar enough to what you do for a variety of scientific computing problems that it makes it. The GPU makes a pretty good platform for a lot of it. So the GPU has a lot of cores that are very small compared to what you would see in an ARM processor, but they're big enough to do useful operations. And the fact that you have a lot of them means that you can take advantage of the embarrassing levels of parallelism that exist in a lot of problems. You also have a memory hierarchy that has multiple levels, multiple different types of memory. Now the bad news is you need to manage this memory hierarchy much more explicitly than you would in an ARM processor or an Intel processor. The good news is if you can do that well, you can run very efficiently and at high performance. In addition to on-chip memories, you've also got access to off-chip memory. Traditionally, they use graphics, DRAMs, but we've also seen recently the introduction of these stacked DRAM memories that provide, high bandwidth and relatively low power consumption. The GPUs we'll see also allow you to access part of the CPU memory, the host memory. And these things are interesting because they give you several precisions of floating points. So you may end up doing your math in floating point, but you don't have to do everything at very high precision. And the less precision you apply to a given problem, the more operations you can do. So why are GPUs useful for neuromorphic computation? because they're highly parallel, multi-threaded, that allows you to take advantage of the embarrassing levels of parallelism. We saw all that data, right? 2 dimensions within a layer and then across the layers. The large number of small computation units is well suited to that. The high memory bandwidth is suited to that. And the fact that it does floating point computation also allowed people to move fairly seamlessly from a CPU-centric computing system to using GPUs. Now, as we're starting to see, when you do floating point, when you do other different kinds of representations, is an important design choice. But the GPU allows you to do some flexibility in that that isn't too onerous. It doesn't require you, for example, to design your own floating point device. Okay, so just as one example, NVIDIA's Pascal GP100 is one of their newer processors. It has several types of units in it. There's a graphics, and these architectures are complex. Quite frankly, I find the documentation provided by both major manufacturers to be less than ideal. Okay? And so the fact that they're complex means that there's lots of little things to worry about. It may take you some time to figure out exactly all the gotchas, amazing things. But to give you a basic idea, you've got a graphics processing cluster, highest level. You've got texture processing clusters. This terminology very clearly relates to graphics, but this is sort of a memory-intensive unit. You've got your streaming multiprocessors. You're doing a lot of your numerical operations. You have memory controllers. So the GP100, you've got 6 clusters. You've got 10 streaming multiprocessors per cluster. You have 30 texture units, and you have 8 memory controllers, each of which is 512 bits. So that's 2 memory controllers per HBM2 stack of memory. That's a lot. Okay, this block diagram shows you the streaming multiprocessor here. So you have 64 cores, each of which will do single precision 32-bit floating point. Okay? If you look here, there's an instruction cache that feeds into an instruction buffer. We'll talk about how you schedule operations here, but you're scheduling the operations. This is a register file. You've got a whole bunch of cores here. This is the texture memory, which in graphics would be used to describe the textures for what things look like, but you can use this memory for other operations, for different algorithms. So each block consists of 32 single precision cores with an instruction buffer. The work scheduler is what schedules when computations happen, and then the dispatch units control the hardware. So the floating point units can run in several levels of precision. There's single precision. There's double precision. Basically, it's going to run half as fast. Well, half as many operations, and 16-bit floating point, in which you basically take a 32-bit unit and split it in half, so they can do 2 at a time. 16-bit floating point sounds limited, and it is, but for a lot of operations that may be sufficient. Okay? So the ability to control how much precision you put down and how much parallelism you're going to get is an important part of the appeal of GPUs. Okay. So just a rundown on the numbers of the GP100. 32 threads per warp. So in this case, thread is similar to what you would mean in a CPU, right? A thread is a unit of execution. Roughly speaking, a thread corresponds to a program counter, right? So you group these, in the terminology, you group these threads into warp, you have 32 threads in a warp. You get up to 64 warps. You can give a multiprocessor, that means 2,048 threads in the multiprocessor. You can have 65,536 registers, 32-bit registers inside the streaming processor. You have that many registers per block. Each thread, though, can only have 255. The block size of a thread is 2024, and the shared memory per streaming multiprocessor is 64 kilobytes. Right? So a lot of these numbers are determined by various aspects of the hardware, how wide buses are, how many, how big decoders are, how big registers are, right? So basically, the GPU designers have made some choices on the ratios you need for between these parameters that support a range of applications, right? So this may not be the ideal choice for any particular application, but they need to support graphics, they need to support different kinds of scientific computation. They've made their choices about how to allocate hardware. Yeah.
So you got 64 kilobytes of shared memory, and then the number of registers is 64 kilobytes. Number of 32-bit registers.
Right. Yes.
A lot of registers.
It's a lot of registers, that's right. That's true. Yeah, you're absolutely right. This is data rather than instructions. Right. But it's also true that any given thread can only have 255 registers. Right? But yeah, you're right. It's a very different balance. It's a very different set of trade-offs than you would see in a CPU. Absolutely. And that's because it's more designed for lots of parallels. You got a lot of threads going, right? That's also very different from a processor, right? So AMD has made a big splash with their new Zen processors, right? So you can buy a processor that has a chip that has 8 processors, 16 threads. That's really, that's a big improvement. My machine at home, which was fairly nice when I put it together 2 years ago, has 4 processors, 8 threads. So the new AMD processors double on that. But here you've got 2,048 threads per multiprocessor, right? And you've got 60 of these streaming multiprocessors on a chip. So that's a lot of threads. So you are absolutely right. This is a very different design style. The trade-off, though, is that you have to do a lot more explicit programming, right? CPUs are designed to make life relatively easy for programmers. Not so true here. Okay. NVIDIA has certainly more visible set of software to support deep learning neural networks. So they have a set of primitives called CUDNN. They have an inference engine called TensorRT. They have a application for video analytics. To support that, they also have libraries for linear algebra. The basic block stands for basic linear algebra subroutines, and then they have another library for sparse matrix. And then they have a library that supports multi-GPU operations. Remember, we saw that AlexNet was explicitly designed to run on 2 GPUs in parallel. So the AMD architecture is conceptually similar, right? Because they're both aiming at the same basic markets. They have a scheduler, they've got a geometry engine, they have a compute engine, and a pixel engine, and there are a whole bunch of these in parallel. From what I've seen, they don't have as much software support directly for neural networks, but they have a lot of support for the usual numerical stuff, right? They have their own package for blocks, for basic linear subroutines. They have another linear algebra package called Magma. They have sparse matrix. They have FFT, random number generator, and they also have some tools for performance analysis. Okay. So NVIDIA has come up with this CUDA programming language, which is not limited to neural networks, right? But you can build neural network coding on top of this. A lot of people use CUDA. It's designed to be scalable across different sizes of GPUs. So it's not, it's related to the GPU programming model, but it's not explicitly tied to a particular configuration. So it's going to be somewhat independent of the particulars of the process. So it has a hierarchy of groups of threads, which is what you need in order, because that's the way the GPU scheduling mechanism works. It has models for shared memory. There are different types of shared memory inside the GPU. And it has mechanisms to allow you to do barrier synchronization. What do I mean by barrier synchronization? Those were good cookies, weren't they? Yeah, okay. Let's work out that sugar. This is a parallel programming concept. What is barrier synchronization? Okay, I'm doing operations in parallel. I have two parallel operations going on, but in order to do the next step, I need to finish both of these. Okay, so the barrier says, this guy's going to run until he gets to barrier, this guy's going to run until he gets to barrier, and then when they both hit the barrier, then we can go on and do the next step. Okay? The CUDA language looks like C. Right, the semantics are, everybody thinks that using the same characters as Dennis Ritchie did means it looks like it's C-like, but the semantics are what really matters, and this is not strict C semantics, but at least it's a familiar syntax. Okay, and it's also designed to support this combination of the GPU along with the host. Okay. So the interaction of the host is important for I/O, and if you're doing very large systems with a whole bunch of CPUs, it becomes important in the operation also. So let's look at the model that CUDA uses for hardware. And so this is built upon the model for recent generations of GPUs. So this is a single instruction, multiple thread programming model. Okay, it's a little more general than SIMD. Okay? The threads don't have to operate in strict lockstep. Okay. So a set of threads, they run same basic code, but because they're operating on different data, they may make different decision points and perhaps take slightly different amounts of time to execute. Okay. We've seen the term warp. A warp is a group of threads. I'm not entirely sure where they came up with the name warp, but that's what it's called. Okay. The maximum number of threads in a warp is determined by the hardware, basically by the size of certain registers. Okay? So, because this is a SIMT model, all the threads start together, but they may not progress at exactly the same pace. Okay? So each thread has its own program counter. But the way to get the best performance out of this is to not let the threads go crazy. Right? The more variation you're going to see in how long they take to finish in the different branches, the longer you're going to have to wait on average for everybody to finish. Right? So part of the goal of algorithm design is to come up with a thread structure that gives you the flexibility you need, but is still controlled enough that you don't wait too long, right? Because if you're waiting for one thread to finish, all the other threads are taking up the hardware and not doing anything useful, right? In addition to wasting time, you're also burning power that's going to cause your chip to run hotter than it needs. Okay, so each warp needs context, right? The program counters all the different things in order to know its state of execution. That context is maintained on chip. That means that you can switch between contexts very, very quickly. Okay? So this is somewhat like multi-threading on CPUs, designed for very low-cost switching. Right? It's unlike switching between threads in an operating system, which is more expensive. Okay, this is hardware supported multi-threads. It does mean, however, that there's a maximum number of blocks and warps that you can have in the GPU at any one time. Okay? Because you have a limited amount of context resources. The execution unit keeps track of the warps. If somebody is waiting, could be for memory, could be for something else, it will find another warp to execute, and on an instruction by instruction basis, try to keep the hardware busy with warps. Okay? Okay. So, given that model, how do you maximize the performance of an application in general, a CNN in particular, on a GPU? Well, first, if you have to communicate with the host, you want to parallelize that with the GPU operations, right? So, if you're classifying a bunch of images, if you read in all the images and then you run the neural network, right? Then the GPU is waiting a lot of the time. Right? If you're reading in one batch of images while you're processing your previous batch, then you're improving your performance. Clearly, you want to maximize the parallel execution of those different convolutions, the nonlinearities and so forth on the processor, on the GPU, right? You also want to minimize the amount of the waiting time, the latency within a warp, okay? So that means minimizing the number of registers that the warp depends on. Makes sense? You want to minimize the use of off-chip memory, okay? Because you have this nice local memory, very fast. The farther you go from that memory, the more expensive it is. And going to the HBM is going to be very expensive. Going to the host is going to be even more expensive. The number of registers per kernel affects the number of warps you can have in the GPU at a time, right? So you say, oh, well, if I just use, a whole bunch of registers in this, that's great. I can run this warp really fast, but that means that you're going to have fewer warps standing by. And what does that mean for your parallelism? It means that if you have fewer warps, the execution unit has fewer ways to keep the GPU busy, right? So there's a trade-off between how many registers you use and how efficiently the execution unit can make use of the hardware. So the memory hierarchy is very important in the GPU. And once again, you have to manage that much more explicitly than you do in a CPU. Okay, we all know that, you know, writing things for caches and so forth is important, but it's much more important in a GPU. Meaning to load data from your device into the shared memory. Right? You want to synchronize all the threads so that the reads don't block each other. Right? You want to, you don't want a bunch of threads going to the same part of memory such that all their access is, but to slightly different locations so that they interfere with each other. You want to process data in shared memory that you can. You want to synchronize. You want to have, that is, have program construct barriers in there to make sure that you understand the interactions between threads. And then you want to, at the end, write results back to device memory. Okay? So you want to go through. You want to go through this. Oh, there we go. Okay. You want to move memory into the GPU. Process it efficiently in the threads with minimum amount of blocking and move it back out. So that you're not crashing the GPU memory system. Okay? So bring it in, process it, put it back out, rather than, you know, read from global memory, write some, read, write, read, write, read, write. Okay? So, the global memory accesses can be ranging from 1 to 16 bytes, 1, 2, 4, 8, or 16 bytes, and these are all aligned accesses. Okay, what do I mean by aligned? They're aligned relative to the to the addresses and the size of the memory, right? So the starting point for, say, a 16-byte block depends upon is basically determined by the upper bits of the memory address. And you can't pick a window, you know, with some weird offset just because it's convenient for you. The alignment is determined by the physical design of the memory. Okay? If you have a two-dimensional array, we're going to talk a little bit more about memory alignment in a few minutes, but they're most efficient when two-dimensional arrays have a width that is a multiple of the warp size. Okay, so now we're relating the memory access patterns directly to the number of threads that are executing in parallel. Okay? Right, remember, the warp is a set of threads, and we're saying that we want, particularly for two-dimensional arrays, we want to basically strike them across the memory. Okay? So as we walk down the second axis of the array, we're going to go this way. But on the first dimension, each section, each thread in the warp gets mapped into a different column of the memory. Okay? The compiler will take care of a few issues for you by using local memory for some automatic variables. So it's not an assembly language, we'll do some work for you. The shared memory is divided into banks, and you can design, so you can design your memory accesses to take advantage of the bank structure to give you some amount of parallelism. constant memory has a cache on it, and the texture and service memory is also cached. Okay? And so that's a certain amount of hardware management. If you can organize your accesses so that what you need is likely to be in the cache, you're going to get better performance. Okay. So what do we do to okay. What do we do on the instruction side? Right. Remember that the number of cycles per instruction can vary widely. As a simple example, doing 32-bit floating point means you can do twice the number of operations in a given amount of time as with a 64-bit floating point. Okay? So we're used to thinking of RISC processors. That's the easy way to think about things in which everything takes everything finishes in one clock cycle, right? We retire instructions one clock cycle at a time. That's not true in this world. You can see wide variations in the amount of time it takes to finish an operation. Okay. And what does that mean for our threads and for our warps? That means that different branches do very different types of operations. It may take different amounts of time to finish, which means that the different threads can be unsynchronized. That means some of them are going to wait while the longer execution paths finish. Okay. So if we want to minimize time in general and we want to reduce the effects of this desynchronization where some paths take longer than others, we want to think carefully about some of these low throughput arithmetic instructions. Okay. So even at the GPU level where numerical precision comes relatively easily, we may want to think about how much precision we need so that we don't use expensive operators for things that don't really need them. Okay? We also want to design our threads so that there aren't that many opportunities for different flow control. Clearly, you have to do that in a lot of cases, but the more different branches we have, the more different execution paths we have, the more problems we're going to have with synchronization. And the more possibilities for conflicts in memory access because everything is desynchronized. So rather than have all sorts of fancy control flow and then having a lot of synchronization points, you're better off having relatively simple control flow so that you can reduce the number of synchronization flows. Okay. So the programming model, now that we've got those pieces in place, provides an array of streaming processors, streaming multiprocessors. You're going to use a C function to define a kernel. Okay? Kernel's a core operation. And then we have n threads that represent n executions of that kernel. Okay? So a thread block is a set of threads in a block. We have a three-component vector that allows us to identify kernels that are executing along several dimensions. So threads within a block can share data and they can synchronize. Okay? So you have to organize your sharing of data, you have to organize the synchronization within your thread block. Okay? Now the next level of abstraction in programming is a grid, which is a set of blocks. The blocks in a grid execute independently. Okay, so you can't synchronize them. So you can do different things, but you can't have different blocks in a grid rely on each other. Okay? So each thread has local memory. Each block has a shared memory that is shared among the threads in that block. The values have the same lifetime as the block. So once the block finishes, you're not guaranteed that the values will be there because they could be used by somebody else. Okay? The grids, that's the highest level of abstraction. Remember, that's the set of blocks. There's a global memory. There's a constant memory. And there's also the texture memory. And that has some fancy addressing modes. Texture memory is designed for sort of, textures can be big, so there's fancy ways for compressing textures and so forth. And that's why you have all these specialized addressing modes. Yeah, so that's right. So in graphics, you know, you've got these patterns, but they also apply compression to reduce the size, which means the different textures are different sizes and so forth. So you have a fancier set of addressing modes than you do at the lower levels of the hierarchy. Are the addressing modes useful in this? In neural networks, I would say only to the extent that it allows you to, you know, select the size of the data representation. Right? So if you say, I only need 8 bits or 10 bits for this part of memory, that's fine. But it's not as, you don't need something as fancy as you do in graphics. But, you know, you're sort of stuck with it, right? Okay, so a slightly higher level of abstraction, OpenCL is a standard that was designed to support heterogeneous computing. I think it's fair to say it was originally motivated by the CPU-GPU combination, but it's also designed to support FPGAs. It has a real C++ API, right? So that you can call OpenCL routines from C or C++. It supports a 4-level memory hierarchy. Global memory, which of course is the slowest, very long latency. There's a read-only memory that can only be is read from the point of view of the GPU or the FPGA. The host can write it, but the other devices can only read it. Local memory is shared by a group of processing elements, and then private registers that are per element. So this corresponds roughly to the memory hierarchy you would see in a GPU. But there's some relationship to what you can do in an FPGA. It also provides you ways to handle vectors, very important, and it also allows you to describe synchronization. Okay, so on top of all this, at an even higher level of abstraction, we mentioned CAFE before. This is a library specifically for neural network development. It's a combination of C++ and CUDA. It has interfaces at the command line, for the Linux command line, Python, and MATLAB. You can run your code on either CPUs or GPUs. For AlexNet, as one example, on a NVIDIA K40, you can run 2 milliseconds per image. Pretty good. Less than 1 millisecond inference on a Titan X, which is a bigger processor, and 20 milliseconds per image on an 8-core CPU. So factor of 10 difference between an 8-core CPU, which is a pretty nice processor, and sort of a mid-range GPU accelerator. And it gives you a pretty abstract programming environment that is tailored for neural networks. So let's think for a minute about the kinds of optimizations we want to do for GPUs, excuse me, for neural networks, and specifically how we would do them on GPUs. Okay, so we want to look at data reuse, which is very important in convolution. We also want to look at loop unrolling. Okay. Why is data reuse important in convolution? Why do you think? What kinds of data reuse do we have in the convolutional operators that we solve? In Alex. Right, but I mean, what values are we going to reuse?
Because the kernel in convolution computing, we use the kernel.
Exactly. The kernel weights we're going to reuse a lot, right? And also, you know, there may be some reuse on the image also, right? But certainly the kernels we're going to reuse a lot, right? Okay. So these authors noticed that the memory bandwidth on a GPU is more limited than what we would ideally like for the convolution operation. That really, you know, dominates the neural network operation. Okay. So they looked at how to optimize these convolutions for GPUs. They want to coalesce the global memory accesses. Right. So you do have to bring some stuff from global memory, but you don't want to access the same location a whole bunch of times. They want to avoid bank conflicts for the shared memory, right? So the shared memory is divided into banks. When we access it, we want to access it once. And they also want to make use of the constant memory to broadcast values. Okay. So they observe that the number of symmetric, the width of the memory for the symmetric processor is a function of the convolution distance, right? So we're doing a set of convolutions at once. In particular, for the Kepler GPU, that value is 2. Okay, so we're going to do the convolutions row at a time. Right, if we have this two-dimensional array, we're going to do a row, do the next row, then the next row. And we want to maximize parallelism in a row. Okay, so because of the structure of the Kepler, we want to have each thread handle 2 pixels per row, where n equals 2, and then we output n times h pixels in a block. Okay? So now we've reduced the number of threads, but we've increased the number of registers that each thread needs. Okay? That's the trade-off that they think makes sense. So this is a figure from their book. Right, so the left-hand side here is unoptimized. You can see that they've mapped 3x3 blocks onto different threads here, right? And that each one, in this case, is offset by 1. Each of those threads is offset by 1. They're saying, in the case of the Kepler, what you can do is combine basically 2 of these into 1. So now the offset between adjacent threads is 2. Okay? So we have fewer threads, each with more registers. That gives us better reuse characteristics, better access characteristics. You have a different processor with different numbers for the number of threads and the memory and so forth. This n might be a different value. Okay, but the same principle applies, but the value of n can vary. Okay? So, in this case, they are sort of working through a whole bunch of constants at once and come up with this nice, clean relationship between the number of threads and the basically width of data that it operates on. Okay? So that's one interesting result, and you'll see the citation at the end. I talked about precision in general. I said that the nonlinearity is a particularly important point for the consider the nonlinearity. This is actually a result that's almost 25 years old now. Other people have done more recent work along these lines, but similar results. Okay? So these guys showed that, well, this plot shows you the error variance as a function of word length. Okay? And they showed that rounding effects are more important than the number of bits and the weight. Okay? And so this feeds into the idea that we've seen in more recent papers that relatively simple nonlinear operations and work well. Okay? So both of these optimizations, the thread layout, the numerical precision, relate to some extent to both classification and training. Let's spend a minute talking about how you can improve the performance of training and what training is. Okay? Because training requires running on a lot of data sets. Okay? There are a lot of heuristics that go into training. There's how often how you're going to batch the training, level of accuracy, and so forth. Let's concentrate here on sort of the basic mechanics of the computation. So, what is the purpose of training? The purpose of training is to find the weights that give us the results we want, right? The weights inside all the network, when we apply them to our input images, they say, okay, this is a dog, right? If we have the wrong weights, it's going to send that picture of a dog and say, oh, that's a horse. Okay. So we need to find the right weights by computing the values and then saying, you need to change the values in order to get the final result to be what you want. So AlexNet, like a lot of networks, is all feed forward. The data flows in one direction only. Okay? Training flows in the reverse direction. We go from the outputs back through the input weights to say, what weight values do I need to get the output I want? Okay. And it's computationally expensive because we can't just do it in one pass. It takes a whole bunch of passes to improve the weights. Okay? So we call it backpropagation because we are propagating values in the reverse direction through the network. That backpropagation is based upon output error, and the basic algorithm, the basic idea that all this stuff is based on, there can be lots of variations, but the basic idea is what's called stochastic gradient descent. At a DARPA meeting a couple weeks ago where they said, you know, this has been done since, what, the 60s? You know, the basic idea hasn't changed in 40 or 50 years. So we're going to update the weight based upon the current weight, based upon some gradient between how the, you know, where the weight is now and where we think it should be, and we're going to have a coefficient there, which we call the learning rate, that determines how much we change our weight for a given change in gradient, for a given gradient. Okay. So, given an output, given an error, this is a slightly fancier form of this concept. The change in the weight depends upon the learning rate, it depends upon the errors, and it depends upon the weights. Okay? And it depends upon the output that we have. Okay? So we're going to apply that, and then we have to apply that delta W to each of the weights. How do we improve the accuracy of training? How do we you know, get the results we want, right? And do it in a reasonable amount of training time? Well, we want to run more examples. We want to increase the number of model parameters. Okay? So this paper talks about making use of two forms of GPU parallelism in particular to help us improve the running time and the accuracy of our training algorithm. So using multi-threading, okay? Spreading the computation across more threads, the GPU, and also using the communication mechanisms across different parts of the GPU and across GPUs themselves. Okay? So they basically observe that the speed of GPU training is limited by the size of the onboard memory. And we saw that GPUs have, you know, good number of registers, but if you have one more value than what fits in your registers, you have a very big cost to go to the next level of the memory hierarchy and get it. Okay? And you can see that we've got more parameters in the back propagation formula than we have in the convolution itself. Right? We've got you know, the learning rate is small, but we've got the outputs, we've got the deltas, and we have. Right? So they actually looked at two different types of parallelism. Okay. In this case, they're sending different pieces of data to different, what they call replicas, right? Different versions, and then they have a sort of centralized resource that pools together the results from the individual replicas and updates everybody's weights. Okay. In this other model, they take the same data, send it out to a bunch of different units, and then have the coordination step. Okay, so these graphs here show the x-axis is the number of processing units they have. In one case, it's machines. In the other case, it's the number of cores. The y-axis is the training time, and this is in hours. Right? So this is a pretty long process. The maximum here is what, 80 hours. Okay? That's 4 days. Hopefully, right? And so The green is the sandblaster, the configuration on the right. The blue and the red are different variations of the down-core operation where they use different pieces of data going into different processors. And the down-core operation settled down to a reasonable result more quickly. Okay? So they are just throwing hardware at the training problem. Yeah, that's right. This is a big, yeah. This is where the computing really goes, is the training. And so when you think about, you know, 1,000 processors here running for, you know, 15 hours, which is what that data point is. Right? Think about the cost of building that data center. Think about the cost of running that data center. Okay? That's why people are interested in, you know, neural network accelerators for data centers. Okay, because these numbers are so huge, right, that it's worth designing a custom processor. Remember that in general, the number of design starts for chips has gone way down over the past 10, 20 years, right? But here's an application that needs so much computation, you know, even a relatively simple hardware design, right, is a lot better than just buying a whole bunch of processors and throwing them at the problem. Okay? Yeah?
What kind of test?
What kind of?
Test. What kind of work? What kind of training or
well, it's doing, the training is this formula. Right? You throw a bunch of data at it, you keep running the back propagation formula over and over. You're just doing this formula over and over and over again.
They should have some spatial purpose. For example, for image recognition or image.
Well, no, the whole point of neural networks is you don't need to do that, right? Now there are variations, right? There are lots of variations, right? But the whole point of neural networks is, it doesn't matter, you know, what type of data you have, what data set you have, you know, use this back propagation and it works. You just throw enough data at it and it works, right? So the programming is simpler, but the cost is these huge numbers. Okay? So if I had the creativity to come up with a specialized algorithm that can recognize a dog, right? If I can A, figure out the algorithm, and B, and figure out how to program it, I can have what amounts to 0 training time and much less execution time, but that depends on me knowing how to design that algorithm and implement that algorithm. Neural networks are interesting to people precisely because you don't have to worry about that step. Okay, and so there's another paper out there that looked at accelerated training on GPUs, and I think the takeaway relative to these other papers is that they needed to have the GPUs communicate with the server and you know, indirectly with each other. And they used MPI in order to do that. MPI is a well-known parallel programming model. Right? So they have this you know, nice programming model that's controlling a whole bunch of GPUs that allow them sort of similar to what we saw in the last slide. They're running a lot of replicas on this range of GPUs. I was at the Computer Vision Pattern Recognition Conference a couple of weeks ago. NVIDIA had a booth there, very nice booth. They had one of their nice boxes with their new GPUs in it. So they had a box, had 4 of these K100 GPUs in it. They had a host processor in there with a lot of memory. They had water cooling for all this stuff. It all came in a very nice black and gold case. Very fancy looking. Take a guess the price. US dollars. Take a wild guess.
10,000.
10,000? Whoa. That's high. So it's about $65,000. Which is not cheap, right? But given the amount of computing you can do with this box that's the size of the box I have at home, right? I mean, physically it's no larger than my home computer. Now, it would increase my air conditioning bill quite a bit. But, you know, $65,000, that's not bad, really. It's not bad, and it gives you a programming model that's not exactly C, but it's a lot easier to design your own chip. That's why people like GPUs for this stuff, right? Because they're powerful enough to give you much better performance, lower power consumption, but they are also simple enough that people who are not hardcore hardware designers can figure out how to program. Okay? So that's finishing a couple minutes early, but that's all I had to say on this topic. If you have any other questions. Yeah. Right. Yeah. Right. So, you know, the weight quantization means basically how many bits you use to represent the weight, right? The rounding effects are determined by how much precision you have within the operation, right? So if we think back to our last set of slides when I talked about the methodology, right? We said that even if you have, you know, 8 bits coming in and 8 bits going out, you may need more precision in the middle, right? That's a version similar to what they're saying here, right? They're saying relatively small weights are okay, but you need to have some more precision in the middle when you're figuring out the operation in order to make sure that you, that's the most critical part of getting the right result. Okay? So that's good in that if you needed big weights, that means more memory, right? Which, if we saw there's a huge amount of memory for all these weights, it would also mean wider data paths everywhere, more interconnect, right? Plus, you would also need, you know, bigger multipliers and so forth, right? This result says that the weights can be relatively small, less memory, smaller interconnect paths, and so long as you have enough accuracy in the nonlinear unit. Well, you know, there's more than one operation going in here, so I don't want to, you know, you're making a very broad statement here about a sequence of operations here, so I don't want to go quite that far, but I think the way to think about it is, you know, the accuracy is needed in the middle of the operation, not at the size of the inputs, or for that matter, the size of the outputs. And that's good news. That's very good news for us, because these operation units, you know, are significant, but a smaller cost than all that memory, all those points. Well, once again, there is a, I'm not going to claim that there's not some art in this, but you can, this methodology we talked about in the first session, you can help with that. There's also other papers out there that I haven't gone over that look at the amount of precision you need for particular nonlinearities for the neural network case, right? And there could be some variation for different neural network structures. But so there are papers out there for particular case, right, in the neural network design space that will say, we found you need this much precision. I think that's the best answer. Yeah, there's a lot of variables to this. You want to make sure you're not oversimplifying, right? But people have looked at that, and in some cases you can do, the weights can be very small in some cases, right? And the amount of hardware you need on the nonlinear unit can be relatively small, but you just have to do the experiments and do the analysis.
Following this question,
Yeah.
is it possible that the best design comes from the mixture of precision?
Oh, absolutely. Yes, absolutely. That's the case in neural networks. We're going to have mixed precision. Absolutely.
Any
Yes.
research on how to
Yeah. People have looked at the amount of precision you need in different spaces. But I think that's the big change in going from GPUs to FPGAs or ASICs, right? It's harder. It's harder, and yeah. Right. Whereas with with an FPGA, you have a lot of freedom, and with ASIC, you have even more. So that's what people have been exploring in the past 2 years. And really, there have been papers coming out like this.
Yeah, we have a talk on
Yeah.
Wednesday.
Right. Good.
Device and device, we have this documentation regarding weight.
Anything else? Okay.
Now, this concludes our morning session, and we have a lunch break without lunch. So please explore our restaurant in Chick-fil-A. Can I come back here once?